Not that they're satisfied, of course. Geochemists are still fine-tuning their estimates of the age of the Earth and looking for more evidence to support or diminish their theories. But really, the only rock I have my eyes on right now is Dwayne "The Rock" Johnson. Hashtag dream. Oh, one other thing. Happy National Chemistry Week. Use the hashtag NCW30years to tell us how you've been celebrating the 30th anniversary of NCW.
I first joined the Geochemistry Division of the ACS as a student, and the programming was so good, and I connected with so many people that I just never left. The community in the Geochemistry Division is really strong, and because we're on the smaller side, the visibility you get is incredible. In geochemistry, students get to give talks rather than posters, and the talks are long enough to allow for meaningful questions and discussions, which doesn't always happen at the other parts of meetings. We do a lot to support our student members and the next generation of geochemists. For example, we award 3 to 5 students for every meeting with the Geochemistry Student Travel Award, which covers their registration fee, and we allocate an even longer time slot for their presentation at the national meetings. For outstanding accomplishments in this field, we award the Geochemistry Medal once every 2 years. The winner receives a cash award in addition to the bronze medallion, free meeting registration, and travel. And we put a symposium in their honor for that meeting. As a division, we are really dedicated to supporting our members through this type of recognition. When you join the division, you become a part of shaping the research and stay informed of what is on the cutting edge. So whether you're writing a research proposal or looking for a job in the geochemistry field, this is an essential group to be a part of. We look forward to welcoming you to the Geochemistry Division of the American Chemical Society.
President of the American Chemical Society and Associate Laboratory Director of the Earth and Biological Sciences Directorate at the Pacific Northwest National Laboratory. It's my pleasure to introduce today's ACS program in a box. Chemistry Rocks, exploring the chemistry of rocks and minerals, where we have gathered expert chemists to guide you through how these fundamental materials are helping the world and improving our lives. Tonight's topic is of great personal interest because my research focused on the role of proteins in biomineralization. During my time in the material sciences department at PNNL, I co-invented a process inspired by biology that allowed us to grow bioactive calcium phosphate layers onto the surfaces of artificial joint implants. By mimicking bone, this innovation has the potential to extend the life of the implant and reduce protection. And going forward, I encourage you to take another step and get involved with ACS. You'll quickly learn that the society is an invaluable resource that will provide opportunities for our leadership skills.
Is anyone like super in love with pop rocks? I have one.
I'll take Adrian. Take whatever you want. Toast to me.
You said you wanted a discussion about a proposal. You didn't want a big thing. This isn't that large.
Come on, put it on. From around the world, and to learn how ACS can help you in your career. And then share your experience with us.
If you haven't done so yet, put in your name for a raffle.
Thank you everyone for being a part of this seminar and enjoying the time.
What is biomineralization? How can it inspire sustainable and novel building materials? We've sent hundreds of PID documents to groups across the United States and around the world. This is your opportunity to introduce yourself to thousands of young chemists participating in this event. You can join the conversation with us and your fellow chemists by using hashtag ACSPID on Twitter, Instagram, and Facebook. Think of it as your backstage pass. Say hello, post photos of your group, and tell us how many you are tuning in. We'll feature the best posts on screen, and you may come away with some free merch. We'll also share CNN articles and other content driven with the hashtag, which you can use to ask questions of our experts as well. Or see the best ones during the live Q&A at the end of our broadcast, so keep them coming. Do not forget to include the hashtag ACSPID. Group leaders, you can use the GoToWebinar chat window to tell us how many are watching in your university or local section. You can also use the GoToWebinar chat window to submit your group's questions. Before we get started, please note that neither CNN or ACS endorse any of the company's products or services that may be discussed tonight. Now, it's time for the opening act. Let's play a little chemistry gemstone tribute dug up by our friends at ACS Outreach. These questions will pop up throughout the night, so get your phones ready and tweet us using hashtag ACSPID if you know the answer. This form of silica is amorphous, meaning it does not form crystals like most gems do. This lack of crystal structure makes it diffract light in interesting ways, commonly called plate coloring. Some people know this material as hydrous silicon dioxide, but what is its more common name? Opal. This can be white, colorless, yellow, or green. When it diffracts light, it can cause rainbow flashes of just about any color, depending on the reason. The most common use of opal is in jewelry, but it can also be found in medicines and cosmetics. Did you know that opal is the national gemstone of Australia, which produces 97% of the world's opal? Drop your geochemistry knowledge on us right now using hashtag ACSPID. Dr. Youngshin Jun is Professor of Energy, Environmental, and Chemical Engineering at Washington University in St. Louis. Let's join her at her lab where she'll discuss the energy-water-food nexus and why minerals matter so much in this vital concept.
As demand for clean water, energy, and food increases, it is critical to study the overlapping relationships between these three finite resources at the water-energy-food nexus. Scientists like Dr. Youngshin Jun at the Washington University in St. Louis are researching ways to increase efficiency and sustainability of processes at the water-energy-food nexus. Chief among her lab's concerns are how minerals involved in these processes can be studied and manipulated to reach sustainability goals.
Hello everyone, this is Youngshin Jun, a professor in the Department of Energy, Environmental, and Chemical Engineering at Washington University in St. Louis. Today, we'll talk about minerals at the water-energy-food nexus. When we are drinking a cup of water, you might think that you are simply consuming water. However, water treatment requires energy consumption. On the other hand, energy production also takes water. All types of energy generations require water. In particular, desalination and extracting groundwater processes are energy intensive. Agricultural activities for food need both water and energy. Let's take a look at California. Rapid socioeconomic development and high population growth resulted in a water shortage problem. We can see this in the green to red color shift in those images taken by NASA from 2002 to 2014, which indicates a significant water loss in California. You can use reclaimed water to replenish the depleted aquifer. It is usually secondary, tertiary drinking water from water treatment plants. The reclaimed water can be injected into the aquifer, and then the water can be reacted with mineral in the aquifer. The aquifer has arsenic-containing minerals such as arsenopyrite, or arsenic nitrate. Oxidative dissolutions can occur and release arsenic when we are withdrawing water. Therefore, it is important to have a good understanding of water and mineral interactions to safely recover the water for use. Furthermore, two water treatment and management processes can be combined. In Orange County in California, the system produces 70 million gallons of potable water per day. Both processes are energy intensive, and when mineral fouling occurs in membrane, this will cause even more energy consumption. As I mentioned previously, minerals play an important role at the nexus. Then let's understand better how they form in a system. Let me take an example of calcium carbonate, since they appear frequently in water treatment plants and pipelines. Calcium ions and carbonate ions are moving around, and they have large enough clusters, then their nucleation occurs in solution. We call this process homogeneous nucleation. This is similar to orange color of faucet water, which contains iron hydroxide particles formed in water. The other mode is heterogeneous nucleation, which calcium carbonate is forming on substrate. This is similar to orange color and iron oxide scale on pipeline. Once the nucleation forms, the mineral will continuously grow. Let me explain further about water chemistry and nucleation. There are many nucleation theories. However, the most basic one is classical nucleation theory. Nucleations occur when the total free energy is lowered enough by having a high negative bulk free energy, which overcomes a positive surface free energy penalty. When the concentration of calcium ions and carbonate ions are high, the cluster size can be big enough to passing critical nuclear size, which satisfies this energy requirement. Thus, ion concentration is important to control nucleation process. Once calcium carbonate forms, they can take multiple polymorphs. Polymorph has the same chemical formula, but different crystal structure. It starts from amorphous calcium carbonate, batrite, aragonite, and calcite, which is the most thermodynamically stable form of calcium carbonate. It can be exist in earth crust, coral reef. If you like a lobster, the lobster shell is calcium carbonate as well. It can also be useful to make paint color brighter and make medicine for us to easily swallow. Of course, calcium carbonate forms at the water energy nexus, such as membrane surface, energy recovery site, and geologic CO2 sequestration. First, calcium carbonate in membrane process. Reverse osmosis is often used for seawater desalination, and calcium carbonate and calcium sulfate mineral fouling of membrane is a common problem. Once they form, it will affect the efficacy and longevity of membrane. Of course, energy consumption will increase as well. As you notice, the seawater contains high concentration of calcium and sulfate ions, and the atmospheric CO2 will dissolve into water, which will increase carbonate concentration. Therefore, calcium carbonate and calcium sulfate can form easily. If we look at the membrane surface, you can see beautiful rhombohedra and flowered shape of crystal. Rhombohedra are calcite and flowered shaped ones are batrite. Needle-shaped one is aragonite and gypsum, which is calcium sulfate. To minimize mineral formation and delay its accumulation, my research group modifies the membrane surface chemistry and creates new membrane from the bottom up. This is commercially available membrane, which is polyamide membrane. We could modify this membrane to have much less calcium carbonate or calcium sulfate inorganic fouling formation and preventing those. And the other aspect is we can just start brand new from bottom up and to create a new membrane, utilizing inboundary abundant material like molybdenum sulfide and or carbon, and to make more effective materials embedded in the structures. And so those are the newly created membranes that we're utilizing regular sugars. Why black? We are going to use the photothermal effect, which means we need to absorb sunlight and making membrane hot and killing microorganisms. We can even make water evaporation from this photothermal effect. Another example is energy recovery site, such as hydrofracking site. Water is obtained and mixed with necessary chemicals and then injected into subsurface environment. By this injection, the shale layers are fractured and natural gas is released from the shale. However, natural gas is not the only thing that comes out. Flowback water is also generated in the process. This can be up to 3,000 cubic meters per day, which contain high concentration of calcium ion. To address this problem, my research group and collaborator worked together on making a new interfacial photothermal evaporator using environmentally abundant minerals that can absorb sunlight and then convert it to localized heat, so we can effectively evaporate highly saline water and condense it to regenerate water to drink. Last example is calcium carbonate formation in geologic CO2 sequestration. Geologic CO2 sequestration is a promising method to reduce CO2 emission from point sources. Once it is captured and injected into subsurface storage site, CO2 will dissolve into the brine and forming calcium carbonate eventually, and store the CO2 for a long time. However, injected CO2 can also react with wellbore cement, forming calcium carbonate. This affects the wellbore integrity. Thus, a better understanding of calcium carbonate formations will help us to design a more effective and safer CO2 sequestration. To study high pressure, high temperature reaction conditions at energy recovery site, we need to make it really high temperature, high pressure. And requires special reactors like this at holding high pressure temperatures. It's holding high temperature and pressure is provided from this high pressure pump. So it can be injected and nitrogen gas or CO2 gas, and this following the CO2 is coming and then kept in here. Operating pressure is about more than 100 atm, and temperature is about 95 and 100 degrees C. It's really high and high pressure temperatures. In this video, I discussed how water, energy, and food are interconnected, and the mineral plays a central role in controlling their sustainability. My research group studies energy-effective water treatment processes and water-efficient energy production. During this process, we like to recover useful resources and to use them. I hope you learn that a better understanding of mineral formations will help us to control their behavior and enable us to have technological innovation through chemistry. Thank you for watching this video. Look forward to meeting you soon. Bye.
Thank you, Young Ship, for educating us about the importance of the energy, water, food nexus. Send your questions for her right now on social media using hashtag ACSPME. And have your host enter your questions into the chat window if you don't have a smartphone. It's time for more chemistry gemstone trivia. This organic gem is an amorphous solid made of calcium carbonate. It has a unique luster and comes in colors from white to black with hints of yellow, blue, pink, or green. What is it? Pearls. We all know their value as jewelry, but did you know that pearls are also used in cosmetics, medicines, and paint formulations? Pearls are most commonly produced by oysters, but can also be found in clams or mussels. Don't call me daughter, but do drop your geochemistry knowledge with hashtag ACSPIB. Welcome back. It's time to make this event a little more interactive. Take the following 3 minutes to meet 2 people you don't know. Introduce yourself and tell them why chemistry rocks. Shake hands verbally as you say hello, state your full name and what fascinates you about chemistry. Then let the other person introduce themselves. Now you only have 3 minutes to go. It's kind of like musical chairs. And a 1, and a 2, and then you know what to do.
A bottle of jacuzzi? Hey, girl.
You just want me to take your phone down, don't you? I know we talked about it.
Argued a long time ago. I've never taken this
Let's take a t-shirt. It's a t-shirt. It's for a bottle.
Popular color is blue, which is caused by trace amounts of both titanium and iron.
Yes.
There's two. Get it, girl.
Sapphire. Although sapphire is a natural beauty, synthetic versions are also extremely valuable. Did you know that artificial sapphires help to make body armor, shatter-resistant windows for armored vehicles, as well as integrated circuits and blue LEDs? Light up the night with your geochemistry knowledge with hashtag ACS PID.
You guys have any questions?
Chemists are coming up with many creative ways to manage levels of carbon dioxide in the air tonight. Entrepreneur Brent Constance of Blue Planet thinks that mineralizing carbon dioxide can provide sustainable and environmentally friendly materials for infrastructure around the world.
Humans are putting out almost 40 billion tons, that's 40 gigatons of carbon dioxide a year. We absolutely need to mitigate 15 or 20 billion tons of that a year. The primary approach that's been taken for the last decade or so is an extension of a practice used in the oil industry, which is to take purified CO2, which is compressed to a liquid and injected into the ground, into an old oil field to enhance the recovery of oil out of the field. This has been expanded to look at going to, say, a large coal-fired power plant, separate the CO2 using an amine process to purify it, because the exhaust coming out is only about 12 or 15% carbon dioxide. Purify it, which takes a lot of energy, and then liquefy it and inject it underground to store it there, where hopefully it will permanently mineralize into a carbon mineral. This approach has seen limited success. There's been literally billions of dollars spent on this approach in the US, in Europe, Canada, and the 10 billion or so tons that we really need to remove haven't even been remotely approached. Most of these projects have been unsuccessful at even getting to 1 million tons. What we're doing is something new. We've identified man's infrastructure as a great reservoir for all this carbon dioxide. The most used construction material in the world is concrete. It's the dominant construction material, and there are about 15 to 20 billion tons of concrete poured every year globally. And concrete is a mixture of rock, Portland cement, a little bit of air, and it's carbon CO2 to rock. So of those 15 to 20 billion
15 and 20 billion.
year, about 80% of it, big gravel. Of that sand and gravel, over 70% of it is limestone, which is simply, most fundamentally, calcium carbonate. All limestones, almost, are derived from the skeletons of marine organisms, like corals, that over geologic time have been lithified and become limestone. The basic processes that form limestone can be adapted to form limestone the same way that stones formed in nature, just much faster. Mineralization is the study of how organisms form minerals. Our bones and teeth are minerals, clamshells, coral skeletons, pearls. These minerals aren't formed the same way as simple geologic minerals. They look different. They're often different crystallographies, different crystal systems. Often they're compound proteins and other organic molecules intercalated into the crystals, and have a variety of very different properties, from high albedo, high reflectance, to super high strength, and other interesting properties which are quite different than their inorganic counterparts. By making limestone and then using it in place of limestone that is otherwise mined and open to mines and transported to a mechanism whereby we can capture very large for a market need that's way over 10 billion tons. So what do we do? Well, the image that you're seeing is a nanoparticle tracking analyzer, which is looking at a phase that we've described here at Blue Planet, a bicarbonate-rich liquid condensed phase. It's a liquid inside a in the liquid that we've learned now is a very important state for bicarbonate and aqueous solutions that can be manipulated to maximize the potential mineralization, and it appears to be used in a variety of organisms that make calcium carbonate. This discovery was key in our ability to rapidly enormous amounts of calcium carbonate. We locate our plants with large emitters of CO2, like coal-fired power plants, and we capture the CO2 using a device that's called a gas-liquid contactor that looks like this. Here's a cutaway section of it. And this contains polypropylene nanotubes, which are a couple hundred microns in diameter with 20 micron pores in it. And the gas from the power plant, after it's been through a heat exchanger, runs through these tubes and exchanges with a capture solution, which extracts the CO2 and is absorbed into the aqueous solution and forms a carbonate compound, one of the carbonate species in solution. And this allows us to remove atmosphere.
Have you tried restarting the computer? The refresh button is perfectly acceptable. Nobody uses the refresh button anymore, man. What's refresh? Ooh, yeah, you take charge, AJ. Oh my god.
Spending money on, which is infrastructure. It's money that's already being spent. And on a global basis, this is important because even though in North America and Europe and Japan and a couple other places we're looking at imposing a tax on carbon, most of the countries in the world will never have a tax on carbon and will never be able to afford a tax on carbon. By contrast, though, all of the countries, rich and poor in the world, are building roads and infrastructure, so it's available to them. That's a really critical factor because most of the increase in carbon dioxide is not going to be coming from North America or Europe. It's mostly coming from the developing world. And we need to enable people to take a rock like this and understand that this is a place where a lot of carbon dioxide can be converted and sequestered into a piece of concrete and stored there permanently. This provides a meaningful, sustainable, and quantitatively attainable solution to really address climate change in significant ways, using the chemistry from how coral skeletons and clam shells form in the oceans or form limestone, to mimic that process to potentially impact climate change on a level that is in the hundreds of millions to tens of billions of tons of carbon removal, which will have a meaningful impact on the change in climate, and do it in a way that it's accessible to everybody in the world, the poor countries and the rich countries.
Thank you, Brent, for sharing your vision for the future of carbon capture technology. Send your question for Brent right now on social media using #ACSPIE. Have your host type your question into the chat window if you don't have a smartphone. It's time for more chemistry gemstone trivia. This gemstone is not a single mineral, but a group of several closely related minerals. It has been used since the Bronze Age as jewelry and as an abrasive. What is it? Garnet. Garnet is very hard, and because of this, it's used in sandpaper and in abrasive blasting. It is also used to make bearings in fine watches. And I've also heard that natural garnet can actually enhance synthetically, like trees.
Like good thing
out there back it up with
She'd be like, Garnett.
Let's discover more about the structure and chemistry of gemstones with a short segment from the YouTube channel SciShow. Host Michael Aranda reveals 8 structural secrets of gemstones and why they are more than just pretty rocks. People value gemstones for all sorts of reasons. They're usually rare, pretty durable, and most of all, they're shiny and sparkly. They can have multiple colors, streaks of light, weird inside-out shapes, and all kinds of other qualities. The things we consider gemstones are often made of minerals arranged into different types of crystals, although a few are made of molecules that are arranged totally randomly. But either way, the properties come from their specific chemical structure. At the atomic level, it's simple geometry, but it leads to some of the most beautiful natural materials on Earth. When you look at a gemstone, probably the first thing you notice is its color. Some gems, like tourmaline and fluorite, can come in practically any color you can think of, and often those colors come from transition metals that are incorporated into the mineral's crystal structure, metals like copper, iron, and zinc. The transition metals are the metals in the middle part of the periodic table. Those elements tend to take on bright colors because the way their electrons are arranged lets them absorb visible light with certain wavelengths. With those wavelengths gone, we see complementary color. Sometimes a specific metal is an inherent part of a mineral structure, so the mineral always takes on that color. Malachite, for example, has copper in its chemical structure, which turns it green. Other times, the metals aren't an inherent part of the mineral. Instead, they're sort of hitchhiking in its crystal structure, occasionally taking the place of whatever element would normally be there. Ruby and sapphire, for example, are actually the same mineral called corundum, with a chemical formula of 2 aluminums and 3 oxygens. When some iron and titanium atoms replace a few of the aluminums, the mineral is a brilliant blue, and that's what we call sapphire. But when the hitchhiking atoms are chromium instead, the mineral turns red, and you have a ruby. But there's more to this color thing, because gems aren't always just one color. Some look like they change color when you view them from different angles, an effect that's known as pleacroism. See, crystals are made up of atoms arranged in repeating patterns. The patterns form blocks called unit cells, which can be different shapes, like cubes or pyramids. Geologists classify crystals by assigning 3 axes to the unit cell. Depending on whether those axes are at right angles to each other and whether or not they're the same length, crystals will have different shapes and properties. It's kind of like the difference between building a tower with cube-shaped blocks and building one with pyramid-shaped blocks. Depending
going to be different. If the axes are all the same length and at right angles to each other, like in a cubic unit cell, nothing very interesting happens to the light passing through the crystal. When the axes are different, the light can get split into multiple paths as it travels through the crystal. Different paths might absorb more of different colors of light. So for example, light traveling along one path might seem more green, and along another it might look more brown. And when you rotate the crystal, you change the path the light takes. So pleochroic crystals seem to change color as you move your head or rotate them in your hand. Depending on their exact geometry, you can get either 2 or 3 different colors. Not all non-cubic gems are pleochroic, but even when they are, the color change isn't always noticeable to our eye. But it's a pretty common property. Sapphire, for instance, is often pleochroic. So is topaz. It's just light interacting with atomic geometry. But it looks awesome. Then there are gems that are attracted or repelled by a magnetic field. You can't just walk up to your refrigerator and stick a garnet to it or anything, but strong magnets will attract certain kinds of gems. In fact, the same transition metals that give gems their color can make them drawn to magnets. Often the metal responsible is iron, but rare earth elements like neodymium can do it too. Those trace elements make the mineral magnetic because they have odd numbers of electrons. The electrons have a property called spin, and 2 electrons with opposite spins pair up and cancel out. But when an electron isn't paired, its spin goes uncancelled and it's free to be attracted by a passing magnetic field. That's called paramagnetism. On the other hand, a material with all its electrons paired up is slightly repelled by a magnetic field because when the electrons move around in an atom, they make magnetic fields of their own, which repel other magnets. That's diamagnetism. Bismuth, for instance, is diamagnetic, so it's always repelled by a magnet. When unpaired electron spins line up parallel to each other, you get ferromagnetism, or a mineral that's actually a magnet. Very few minerals are ferromagnetic, but hematite is one example. Sometimes a gem that's normally repelled by magnets will have bits of iron inside it, which will make it attracted to magnets instead. So magnetism isn't a perfect tool for figuring out what a gem is made of, but it's often a helpful clue. Sometimes you'll see gems cut into facets, but other times they'll be polished into a round shape called a cabochon. And sometimes a round polished gem will look like it has a bright streak of light across its surface, like the vertical pupil in a cat's eye. It's called chatoyance, and it happens because of little thread-like pieces of a mineral, like rutile, inside a gem, what scientists call silk. As these crystals form, the impurities are forced to line up along the axes of the crystal structure, so the pieces of mineral end up parallel to each other. Those parallel pieces reflect light in a way that creates a bright line perpendicular to the threads. And it's not just gems that do this. A spool of silk thread will do the same thing, where there's a streak of light perpendicular to the wound-up thread. But unlike a spool of thread, gems can have inclusions going in different directions based on the crystal structure of the mineral. That creates a streak of light perpendicular to each axis, which looks like a star with 4, 6, or even more points. The star effect is called an asterism. When a gem has these threads, cutting it into facets might make it look kind of muddy, but when it's polished into a round shape, you get gorgeous streaks of light. Polymorphic minerals don't always have the same structure. Even if they have the same chemical composition, the temperature and pressure when they form can lead to different shapes. Carbon is probably the most famous example of this. Depending on how its atoms are arranged, carbon can form soft, slippery graphite or basically indestructible diamond. Silica, the mineral that makes up sand and quartz, also has lots of different polymorphs. Its molecular formula is always the same: 1 silicon atom and 2 oxygen atoms. Its molecules form tetrahedral shapes. That's a triangular pyramid, or D4 if you're into tabletop RPGs. Tetrahedrons can stack into different shapes as changes in temperature and pressure jiggle them around. At the temperatures and pressures humans find comfortable, silica makes the alpha, or so-called low, form of quartz. But as temperature and pressure increase, it can become things like cristobalite, which is found in lava flows, or stishovite, which is in meteorite craters. Even a single polymorph of silica can take on a huge variety of forms. Alpha quartz can look like scepters, rounded pebbles, or clusters of needles. It all depends on the growth conditions, like how fast the crystals form, how much space is available, and how much material there is to make crystals. The unit cells stack together in the same way, but sometimes an impurity will cause them to take off at an angle, or make them more likely to stick to one part of the crystal than another. Quartz is so varied that tons of gems like amethyst, chalcedony, agate, and citrine are all made of silica. Organic matter can be slowly replaced by minerals to become a fossil. Often, the mineral involved is kind of drab, but sometimes the conditions are just right to produce something spectacular. And in rare cases, petrified wood, shells, teeth, or even bones of extinct organisms are made of opal. Opalized fossils are most often found in Australia, along with most of the world's opal in general. One of the most famous specimens is a pliosaur nicknamed Eric, an almost complete marine reptile preserved in opal. Like quartz, opal is made of silica, but unlike quartz, it doesn't have a crystal structure. Instead, it's made of little spheres of silica all bunched together. These tiny spheres scatter light, giving opal its characteristic rainbow sheen. Geologists have a few different models for how opal might form, but it could come from silica weathering out of rocks in an acidic environment. Australia used to be partially covered by an inland sea, and as that sea dried up, it left acidic, silica-rich gel behind. Bits of silica settled into the gel and then grew into spheres that make up opals. Sometimes that gel was stuck in bones or bits of wood that had already started to fossilize, so the silica trapped in there formed opals in the shape of those organic structures. The resulting fossils have both aesthetic and scientific value, and in 1993, Eric the pliosaur was almost made into jewelry by a broke owner looking to sell and potentially break up the pieces. But a crowdfunding campaign rescued Eric and got him a place in the Australian Museum. Hopper crystals are probably some of the strangest looking crystals. They're shaped into a weird stair-stepped hollow kind of pyramid known as a hopper. The shape comes from a quirk of chemistry as the crystal is forming. When the growth rate and saturation of the crystal forming solution is just right, new molecules will tend to be more attracted to the edges of the growing crystal than the inner flat surfaces. That makes the edges grow out of control while the flat faces stay mostly the same. So the crystals grow in a lopsided way that leads to that fascinating inside-out shape. Bismuth hopper crystals have to be grown in the lab, but hopper crystals have also been found in nature, in minerals like rose quartz. Bismuth is actually pretty easy to get your hands on. It has a very low melting point. So you can actually try to make your own hopper crystals if you're feeling adventurous. Some materials that are culturally prized as gems aren't minerals or gems in the strictest geological sense. Things like amber, jet, coral, and pearl. Instead of being made up of crystals, all these materials have a more amorphous chemical structure, and they come from living things. That's why they're called amorphous organics. But the way they form makes them look a lot like classic crystal gems. Amber is fossilized tree resin and can actually preserve organisms that get stuck in it. When the tree resin gets buried in calm, wet, low-oxygen environments, it slowly turns to amber. Jet is practically the same thing as coal in some ways, but while coal forms in big seams from huge amounts of plant material, jet is formed from small bits of wood that get buried in sediment and compacted. Jet can be cut and polished to a gem-like shine, but it doesn't have a rigid crystal structure. At a microscopic level, it can actually preserve the cellular shapes of the plant it used to be. Coral is made up of small colonial animals with calcium carbonate skeletons. The skeletons are usually white, but the precious coral that's often considered a gem is a species that includes reddish-orange carotenoid pigments. Pearls contain a mixture of protein and calcium carbonate secreted by certain types of mollusks. Different species will produce different colors of pearls, and impurities in the water can also affect the color. Like all of the gems on this list, amorphous organics look the way they do because of the way their atoms are arranged. The regimented structure of a crystal and the laid-back chaos of an amorphous solid both affect the way they interact with light, magnets, and other materials. It's the sparkliest kind of geometry. Thanks for watching this episode of SciShow, which was brought to you by our patrons on Patreon. If you want to help support this show, just go to patreon.com/SciShow. And don't forget to go to youtube.com/SciShow and subscribe.
It's time for more chemistry gemstone trivia. This silicate mineral containing aluminum and fluorine was named after an island in the Red Sea, thought to be the place where it was first mined. The ancient Greeks thought it had powers of invisibility, and ancient Romans thought it could improve eyesight. Name this mineral, which also happens to be my birthstone. Topaz. This mineral is typically red, yellow, pale gray, reddish orange, or blue brown. There are even colorless varieties that can be colorized by coating the mineral with metallic oxide. In fact, the topaz you find in store-bought jewelry may have some lab chemistry to thank for its color. Drop your geochemistry knowledge on us right now using hashtag ACSPIB. In a few moments, we'll be starting our live Q&A, so if you haven't already, send in your questions now.
Why are you so beautiful?
Okay, let's do some more drawing. Okay, so this is going to be for the last koozie, which is a neon one. Woo! Alright, so now we're on to these water bottles. Yeah. You're excited to say National Chemistry Week, Marvin? Marvin! And the second water bottle. Anna? Amy's going to help me with this one. It's just a bracelet, so we're not going to draw.
Welcome back. Remember to keep sending your pics to hashtag ACSPIB. Our largest groups tonight were Radford University with 48, Tennessee Tech University in Cookeville, Tennessee with 39, Mississippi College at 35, and 7th University in Indiana at 40. UAB Parkville with 60, Birmingham, Binghamton with 36, Chattanooga State at 40, North Carolina University at 40, and Carolina University
at the Duquesne University in Savannah, Georgia. South Texas College had 7 and 4. We had Morgan Christian at Libertyville High School in Libertyville, Illinois. What's up, Libertyville? Southeast Missouri State University had 45. All right, and now we're getting to the largest groups. Buffalo Student Town had 100, and so did the University of Louisville. But tonight's biggest group was at the University of Alabama, Birmingham. We had 121 viewers. Thank you so much to all of you for tuning in. I just want to give a shout out to these wood listeners. Kenzie says, chemistry rocks, but contrary to popular belief, it does not roll. Maddie says, chemistry rocks, almost more than pizza, hashtag ACS Gabby. And congrats to Western Maryland ACS, who was first to get the Opal trivia correct. Also congrats to, oh my gosh, that's a lot of numbers, at PP1877839, who was the first person to answer our other GMI trivia. And we've got some questions now for the Q&A. So I'm joined again by Young Shin. Are you ready to take some questions from the audience?
Yes, I am ready.
Awesome. All right. So the first question comes from Kristen. Can you describe how invasive carbon dioxide sequestration is to the environment?
So I think that is the question comes from because we are applying high pressure, high temperature systems, but actually underground and subsurface environment is automatically high pressure, high temperature. But what we are injecting is high quantities of CO2 and pressurize them into the system. While we are releasing some of the brine and we can offset of the pressure, it could be maintained. So this is engineering problem. Of course, there might be dissolutions happening, so we need to monitor the chemistry environment there in the subsurface environment. However, we need to consider about mineralogy. So that's where we place the mineral rocks. And so we need to consider about mineralogy, the fair side, and also whether we're going to have earthquake in that region. And in the case we are not going to do it. And however, at the end of the day, if we don't address the CO2 in large quantity, which is the largest quantity we can sequester at once, and or large quantities, and that is the only way to do it at this time point. If we can develop the good method to do and sequester or convert the CO2 into more meaningful chemicals, that is future generation. I hope you guys and girls can do this, and in that case we can actually minimize injection of CO2 in the underground, and we can convert CO2 into more meaningful resources. Hopefully that answered your question.
I think that's a great answer. Thanks so much. Question from Joseph. He asked, how effective is the polyamide membrane for forward osmosis processes?
So polyamide membrane is commercially available membrane. So if you look at the video, and the left-hand side is showing that unmodified polyamide membrane, it is actually fouling non-resistant, not resistant, non-resistant. So 2 years later, if you're thinking about 70 million gallons per day of Orange County, and you have to change your membrane. And what my research group is trying to modify sulfate charge and their structures to extend the longevities. If we have to change it into 2 to 3 years, and we like to change it to 3 and 4 years, we can save some monies from it. And because we know the polyamide membrane is not the best membrane, so we like to start from the brand new membrane. And so we can utilize my collaborator, Dr. Singa Mananis from my institutions and my research group working together and build bacterial nanocellulose combined together with photothermal materials, which is mineral, like molybdenum sulfide. And then we mixing together, making perfectly operatable membrane. That is maybe new generation membrane we can replace. Hopefully we can replace polyamide membrane.
Gotcha. And we talked a little bit offline about some of the work you've been doing here, but can you describe some of the most promising results and some of the lessons you've learned developing these membranes?
So because we use membrane to have a desalination process for example, the seawater desalinations. However, seawater desalination is not the only water that we have to treat. So like hydrofracking site, we have, as you saw the video, 3,000 cubic meters per day of huge quantities of water is coming out. And this has so much saline water, and there is other things exist organic compounds, and also useful resource there. So if we can effectively evaporate water, and then we collect the water and drink it, and the remaining surge we can use for resource recovery. So that's actually, we can do that.
Great, thanks so much. Jonathan asks, what is the cost of mineralization of CO2?
I wish that I can actually answer that one more quantitatively, and because I'm in the engineering department while I'm studying mineral, and but depending on situations and how we capture the CO2, clear answer is it is expensive. However, like Brent Continents actually mentioned that it can capture the CO2 and convert from waste to carbonate, which can use for cement materials that will offset the cost of it, so we can utilize that process. Yes, it is the expensive process. However, it can visual issue of CO2. At the same time, it can actually generate useful materials. So this is called as like upscale, upcycling, utilizing some of the waste we thought, but now we can use it for useful material.
I think it's a sort of a balance, right? So we heard about putting CO2 into concrete. Once the CO2 is there, how long does it stay there?
Actually, unless we don't dissolve it, it will just stay there. And because we consider as carbonate formations and underground geologic CO2 sequestration, that is most stable form, most safest form of CO2 sequestration. Once the CO2 dissolves into the water, and then carbonic acid and become bicarbonate and carbonate, and they will capture the calcium carbonate as a solid form, then they will stay as a rock. And however, if you are exposing this into acid rain, then it will want to dissolve it again. So, however, that have the same problem for regular cement. Regular cement is also, if it is exposed to acid rain for a long time, it will become dissolved. And also, like statue you see, and some statue does not have nose, and because of dissolution of their surface, because they are calcium carbonate. So same problem exists, but that would be safest one to store the CO2.
I see. And anything you can do to protect it from dissolution? Is that an area of research that people are looking into?
That's a really cool question, and because my research group is trying to study, is there any way to minimize dissolution of calcium carbonate inside of cement, because calcium carbonate layer is oftentimes acting as protect layer of cement. Even we are not talking about the calcium carbonate cement as a commercial use, and regular Portlandized cement interact with atmospheric CO2, and they will convert somehow the calcium carbonate. That layer is protecting further dissolution from acid rain. So if we minimize calcium carbonate dissolution, and we can protect the layer further, so we have used some sulfate and organic compounds to minimize the surface dissolutions, and by utilizing reactive transport model to predict how much surface area is reacted by acid rain or CO2 exposure. So that is active research area. I hope some of you are participating in that research too.
Awesome. Thanks so much. We have time for a couple more questions. Here's a personal one from Iman. I hope I'm saying that right. What's your favorite gemstone and why?
That's a great question. I like rhodochrosite. I'm not sure whether you guys know about rhodochrosite. Rhodochrosite have rhodo means rose color, and rose color carbonate mineral, manganese carbonate. Manganese carbonate actually have rose color, and it's gemstone. At the same time, that was my thesis studies and dissolution of rhodochrosite and generating manganese oxide. So that's why I like rhodochrosite, and I have jewelry and that I to wear too.
That's really cool. We had a question actually coming a little bit earlier that I think a lot of young chemists might want to know the answer to. You study, minerals, geochemistry, environmental chemistry. What jobs are out there for people interested in those fields?
Maybe this seems to be too positive or too optimistic, but I hope you all optimistic and too positive. It doesn't hurt. And I thought that we don't need to define any limitations of a boundary. And this is a time point that we don't need to make a boundary at all. So if you're thinking as a trained as mineralogist or geologist or environmental chemist or material scientist, but they share the same thing. So only language is slightly different. Like you learn the language English in Korean and from Korea and from Korean or Chinese, and you just learn language and you can communicate with other party. Same way, if you learn the language between the material science people and geology people and engineering people, you share, for example, crystal. And that could be crystallographies could be shared in way chemistry and geochemistry. And sometimes geochemistry, crystal we call as mineral, more specifically, and mixed phase would be rock. And we also say utilizing crystallographies, tuning the material, so that it goes to material scientists. So there is no boundary at all. So if you are really interested in material science, even you did geochemistry, totally okay. So you are a material scientist, but you like to know better about geological context and geochemistry, totally okay to change your field. So there is no boundary. That is important key point. And what I'm thinking about, someone who has good knowledge about crystallographies, mineralogies, and they could work in academia, of course, national lab and industry, and start up. Like our research group and with collaborator, we are working together utilizing environmental abundant materials to generate new membrane. Once we make new membrane, we need to scale up. Then we have to sell it. So it is actually everything is continuum, not just only from I'm generating this and then disappear. It's not the case. Now generate it, scale up, and sell it. So if you are not making any boundary, your job is everywhere. I hope that answered the question.
Absolutely, it's another great gem. Thank you so much for the advice. Do you have any final thoughts to share with our audience tonight?
I really enjoy this experience, and I hope that I can see you in person. And although I remotely sense that how many of you participate. And but if you have other questions and you know my name, if you Google and you can find my name, hopefully we can catch up in ACS meeting in New Orleans. And theme topic is water, energy, food nexus. So I think this is a perfect ground we can actually work together and say hello. That is my final words.
Thank you so much. That's fantastic. Thank you so much for joining us. And we actually do have some hashtag ACS PIB breaking news. University of West Florida has a rock solid group with 134 students watching. So this great showing all around. Thank you all so much for tuning in. Thank you again, Yunshin, for joining us, for sharing your work and answering our questions. Would you like to wave goodbye to the audience? Thank you. Special prize. Very special thank you.